Every atom in your body is caught in a relentless, non-stop cosmic spin. Galaxies twist, planets revolve. If everything is always moving, why do we feel absolutely nothing? The key lies in a law written 300 years ago, and a spin that began before light itself. Our solar system races through the galaxy at nearly 500,000 miles per hour, with the Earth turning over 1,000 miles per hour and orbiting the Sun 93 million miles away. Yet, despite this incredible motion, we feel completely motionless. Our heartbeat doesn't tremble. Our breath remains steady. What if this stillness is the greatest illusion of all? What if time itself is merely an echo of a deeper rotation that began before atoms, before light, before memory? From the smallest electron to the largest galaxy clusters, everything in existence spins. Atoms rotate, planets revolve, galaxies twist in vast spirals of light and dust. Some cosmological models even suggest the universe itself might have a subtle global rotation. The key to understanding this paradox lies in inertia, a fundamental principle of physics described by Isaac Newton in the 17th century. An object in motion stays in motion unless acted upon by an external force. This law explains why we don't feel the Earth's endless spinning. Your body, the surrounding air, the oceans and mountains all turn together in a single silent rhythm. To perceive motion, you need a difference, a contrast. But when everything moves in perfect synchronization, stillness emerges. The coffee in your cup doesn't ripple. The air doesn't drag. The stars appear frozen. It's a profound paradox of motion and calm, inviting us to explore the deeper mysteries of our spinning universe. Tonight, we drift into this mystery, asking not just why things move, but why nothing can stop moving. Close your eyes and let the sound of the cosmos hum beneath your skin, following us into the spinning heart of everything. Earth's spin is an ancient, smooth, constant motion. Our senses miss it entirely, even though it's always happening. We move together with everything around us, gliding through space without feeling any shift. Neil deGrasse Tyson captures this beautifully, describing our planet as a space rock orbiting a star within a galaxy moving through the universe. Our inner ears, evolved for walking and running, can't detect this steady, vast movement. We feel a car's start, but not its cruise. Scientists have ways to prove this hidden motion. The Foucault pendulum, first demonstrated in 1851, swings freely while the ground beneath slowly turns. In museums, you can watch time and motion merge with each gentle swing. This isn't just a curiosity. The Earth's rotation is crucial. It defines day and night, stabilizes the planet's magnetic field, and shields us from solar radiation. Without rotation, one side of our planet would burn, while the other freezes. NASA's Goddard Space Flight Center reveals that this rotation is gradually slowing. The moon's tidal pull adds about 1.7 milliseconds to each century's day. Astronauts experience this phenomenon dramatically in orbit. Traveling at 17,500 km/h and circling the planet every 90 minutes, they feel no resistance inside their spacecraft. Motion becomes indistinguishable from stillness. It's the same principle that lets you sip tea on an airplane moving 500 mph. You and the plane move together. This uniform motion is universal. Only sudden changes like turbulence interrupt our perception of movement. We're always in motion, yet we feel stationary. Our evolved senses work on small scales, not cosmic ones. We call a spinning, moving rock home, without sensing its incredible journey. When we look deeper, rotation isn't just an earthly phenomenon. It's a cosmic dance, happening everywhere, all the time. mostly unnoticed by us. Dwarfs stars form from collapsing clouds of gas and dust. As they shrink, they spin faster, a principle of conservation of angular momentum. It's the same law that makes a figure skater spin more quickly when pulling in her arms. Every plane inherits this momentum. The Earth's 24-hour rotation is a fossilized remnant of an ancient whirlpool of creation. The Sun itself spins once every 27 days, dragging its magnetic field through space like glowing threads. Our galactic home, the Milky Way, turns once every 230 million years, carrying hundreds of billions of stars in a spiral dance that began long before our planet existed. The James Webb Space Telescope has captured galaxies so distant that their light has been traveling for over 13 billion years. Even these primordial galaxies show signs of rotation. ESA scientists studying these early formations found subtle differences in light. One side slightly red-shifted, the other blue-shifted, a telltale signature of spin. It seems the tendency to rotate is written into the universe's DNA. But how can everything be spinning and yet feel so still? Part of the answer lies in relativity. According to Einstein, there is no absolute motion, only motion relative to something else. From our perspective on Earth, we are at rest, and it is the universe that moves. From another frame, the opposite is true. This symmetry keeps physics consistent and makes our stillness an illusion of perspective. In deep space, astronauts aboard the International Space Station orbit Earth at nearly 5 meses, but experience weightlessness, not motion. Their sense of down changes every 90 minutes, yet their minds adapt. We too are passengers in motion, adapted to calm. Our stillness is a form of survival, a balance between what our senses can bear and what the cosmos demands. If we could somehow feel the motion of the Earth, the pull of the Sun, the drift of the galaxy, our perception of time itself would unravel. As rotation defines days and years, it also defines the heartbeat of the cosmos. Time, as Carl Sagan once said, is woven into the very fabric of the universe, and we are the thread. The quiet you feel now is not the absence of motion. It's the harmony of everything moving together. So when you lie down tonight beneath the invisible turning of the stars, remember this: you are not standing still. You are gliding through a cosmic river gently, constantly, endlessly. Each moment of silence holds the universe moving so smoothly that you barely notice. In this perfect balance between motion and stillness, life finds its quiet rhythm. You're spinning, always have been. Take a slow breath. Everything moving together creates the silence you hear. Let's trace back to the moment before motion began, diving deeper into this story. Who set the universe spinning? And if you could turn back time, not just centuries or millennia, but right to the first second after the Big Bang, what would you witness? Would light exist? Would sound emerge? Or would there simply be a sudden motion, a swirl, a twist representing the very first rotation of everything that would ever exist? This isn't just a philosophical question, but a physical one. It's buried deep within cosmological equations, hidden in the earliest moments when matter, energy, and space itself began unfolding. Astronomers refer to this as the Planck era, a window so early, within 10 to the power of 43 seconds of the Big Bang, that our current physics laws cannot fully describe it. What we can infer suggests something extraordinary. The universe might not have been born in silence, but in a gentle rotation. Scientists studying the cosmic microwave background, the faint afterglow of the Big Bang detected by satellites like WMAP and Planck, have discovered tiny temperature irregularities, small ripples only a few millionths of a degree apart. These patterns reveal the early universe wasn't perfectly uniform. Slight differences emerged that would eventually grow into everything we now see: galaxies, stars, planets, and life itself. Some researchers noticed something even more intriguing: a faint alignment, a large-scale twist in the distribution of these ripples. They named it the axis of evil, a mysterious pattern suggesting the universe might have a preferred rotational direction. According to NASA's WMAP mission data and follow-up observations by ESA's Planck satellite, this alignment could mean two things: either a subtle measurement artifact or evidence that the entire universe once spun. If true, that initial spin might have shaped everything, from galaxy spiral arms to the very arrow of time itself. The key might lie in quantum fluctuations. Tiny fluctuations in energy occurred when the universe was smaller than an atom. Even in complete emptiness, these variations naturally happen. Quantum fields are never perfectly still, according to NASA's Goddard Space Flight Center. They jitter. During the Big Bang, these jitters were stretched and amplified by cosmic inflation, a brief but explosive expansion that made the universe grow faster than the speed of light. This rapid stretching might have transformed some quantum jitters into swirling motions. The first inflation theory, proposed by physicist Alan Guth in 1981, explains why the universe appears smooth and uniform while still containing structural seeds. Recent data from Planck and BICEP-2 experiments suggested subtle rotational modes called B modes might have existed in primordial gravitational waves. These tiny space-time curls could be the universe's first rotational fossil record, showing the Big Bang was not just an explosion, but a twisting birth that imprinted spin across every matter scale. As the universe expanded and cooled, matter began forming. First quarks and gluons, then protons and neutrons, then atoms. Each carried tiny amounts of angular momentum. When gravity later gathered them into clouds and galaxies, this ancient angular momentum was conserved, similar to how a figure skater spins faster by pulling in her arms. In physics, motion must originate from motion. The first spin, however small, had to exist from the beginning. Astronomers can now see rotation's fingerprints in distant galaxies. In 2011, Harvard-Smithsonian Center for Astrophysics researchers analyzed over 15,000 spiral galaxies, finding a subtle rotation direction preference that might trace back to the early universe's spin. While not yet conclusive, this cosmic handedness hints that our universe might not be entirely random. There could be a hidden rhythm, a silent turn that everything still follows. Even dark matter, the invisible scaffolding holding galaxies together, might carry a spin signature. NASA's Jet Propulsion Laboratory computer simulations show dark matter halos twisting and rotating over billions of years, guiding visible galaxies within them like whirlpools directing leaves. Without this rotation, galaxies would struggle to form. The universe's primordial motion seems to echo through time, with spinning as a fundamental characteristic from the very beginning. What sparked this initial rotation? Physicists point to a concept called symmetry breaking. In the universe's earliest moments, fundamental forces like gravity, electromagnetism, and nuclear interactions were a single unified entity. As temperatures dropped, these forces began to separate. During this process, tiny imperfections emerged, asymmetries that would become crucial to existence. The European Space Agency explains that these microscopic irregularities enabled structure, motion, and spin. A perfectly balanced universe would be static, but slight imbalances allow for dynamic movement. This principle manifests everywhere, in galaxy rotations, atomic movements, and even the left-handed preference of neutrinos. Nature isn't perfectly symmetrical, and that small flaw drives everything's rotation. Scientists have investigated whether the entire cosmos rotates. In 2020, astrophysicist Lior Shamir analyzed over 200,000 galaxies and discovered that galaxies in one sky hemisphere tend to rotate more consistently in a specific direction. This doesn't mean the universe spins like a toy top. Instead, space-time might have slightly twisted during its expansion, a subtle movement that could ripple across billions of light years, potentially shaping the universe's entire geometric structure. Quantum mechanics reveals that spin is intrinsic to matter. Every particle, electrons, protons, neutrons, carries an inherent spinning property. This isn't physical rotation as we imagine, but a deeper mathematical characteristic. NASA and other space agencies continue mapping the universe to test these theories. The James Webb Space Telescope is already capturing light from galaxies formed just 300 million years after the Big Bang. Some of these ancient systems display organized rotational patterns too early to be coincidental. The seeds of spin were planted almost instantaneously. The universe didn't learn to rotate. It was born turning. From the grandest cosmic scales to the tiniest quantum interactions, movement and rotation are woven into the very fabric of existence. Onto rotation encoded in the wave function itself. Physics has always carried a hidden motion, spinning within its core. The basic blueprint of existence isn't something added later, it's intrinsic. As physicist Richard Feynman noted, spin isn't about literal rotation, but a fundamental property like mass itself. Look up at the night sky, and you'll witness this inherited motion. Every cosmic structure, galaxies swirling, planetary orbits, even photons of light, descends from the first cosmic rotation. Without this primordial spin, matter would remain scattered, stars would never form, and time would lose its rhythm. Motion isn't an accident, it's the universe's heartbeat. We might never pinpoint exactly what triggered the first spin, but evidence whispers of its eternal presence. Cosmologist John Taba eloquently captured this, explaining that the universe remembers not through words, but through light patterns. These patterns bear the faint signature of the first motion, a twist older than time itself. So when we ask who set the universe spinning, the most honest answer is that the universe was never taught to move. It was born in motion, spinning from its very inception. The atoms in your body still turn with that initial impulse. From the tiniest electron to the Milky Way's grand swirl, rotation continues unbroken for nearly 13.8 billion years. We aren't separate from this motion. We are its continuation. This naturally leads us to a compelling question. If rotation shaped the universe's birth, could it also be responsible for life's existence? Consider Earth. Without rotation, it would be a lifeless, static world. One side eternally frozen, the other perpetually scorched. But spinning transforms our planet into a living, breathing entity. Every sunrise, wave, and gust of wind emerges from an ancient turn that began 4.5 billion years ago. Earth's rotation isn't mere movement. It's an intricate engine sustaining life itself. From the magnetic field protecting us against cosmic radiation to the temperature cycles nurturing oceans and clouds, rotation sculpts our world in both visible and invisible ways. The Earth completes one full spin every 23 hours, 56 minutes, and 4 seconds, a duration scientists call a sidereal day. This steady rhythm is an invisible metronome that synchronizes every biological and environmental cycle on our planet. Every plant, animal, and ocean current moves to its beat. At the heart of this rotation lies the fundamental alternation of day and night. Sunlight gets distributed across the planet's surface, creating temperature differences that drive wind, currents, and weather patterns. Without this daily spinning, one hemisphere would burn under constant daylight, while the other remained frozen in perpetual darkness. A violent storm zone would separate these extreme regions. Because Earth rotates, the sun rises and sets, allowing energy to spread evenly enough to support stable climates and habitable zones. This motion extends far beneath our feet, where the planet's liquid iron core moves and churns, generating a magnetic dynamo. NASA's magnetospheric multiscale mission explains how the Earth's magnetic field emerges from the motion of molten iron within its core. This field acts as a shield, deflecting the solar wind, a constant stream of charged particles emitted by the sun. Without this protection, those particles would strip away our atmosphere, much like what occurred on Mars. The red planet spins similarly, but lost its molten core motion long ago, resulting in a dry, frozen desert with an eroded atmosphere. On Earth, this magnetic field creates more than just protection. It shapes the auroras. These soft, glowing light curtains near the poles are not merely beautiful, they are visual proof of an invisible protective force. Where magnetic lines interact with charged solar particles, light emerges as a reminder of our planet's powerful rotation. The spin's influence reaches further, governing atmospheric dynamics. Because Earth turns, air moving from the equator toward the poles curves, a phenomenon known as the Coriolis effect. This effect generates vast spiraling systems of winds and currents that define global weather. It explains why hurricanes spin, jet streams flow, and ocean currents carry warm and cold water across the globe. Without the Coriolis effect, weather patterns would collapse into chaos, preventing storm formation and disrupting global climates. Earth's rotation isn't just a simple planetary movement, it's a critical factor in shaping life and climate. A planet's spin determines how energy and temperature are distributed, with dramatic consequences for potential habitability. Different rotation speeds lead to wildly different planetary conditions. Slow-spinning planets can have one side scorching hot, while the other remains frozen, while faster rotations might generate extreme winds that disrupt atmospheric stability. Earth's 24-hour cycle represents an almost perfect balance. Our planet's rhythm has profound biological implications. Every living cell carries an internal molecular clock synchronized to this daily cycle. This rhythm governs fundamental life processes, from plants opening leaves to bird migrations and human sleep patterns. A disruption in rotation would fundamentally break this biological harmony. The Moon played a crucial role in establishing this rotation. Billions of years ago, a massive collision with an object called Theia dramatically increased Earth's spin. Over time, the Moon's gravitational influence has gradually slowed this rotation, transforming our days from approximately 6 hours to the current 24-hour cycle. Planetary stability depends on this delicate balance. Tidal forces between Earth and the Moon help maintain our axial tilt, preventing extreme climate variations. NASA's Gaia mission confirms how essential this stability is for long-term planetary habitability. Other planets showcase rotation's dramatic effects. Jupiter, spinning once every 9 hours and 56 minutes, generates ferocious jet streams and storms like the Great Red Spot, a hurricane larger than Earth that has persisted for centuries. Here, rotation creates both chaos and stability. Even now, our planet's rotation continues to change. tidal interactions slowly lengthen our days by about 1.7 milliseconds per century, a reminder that our world's fundamental rhythms are constantly, imperceptibly evolving. The spin of a planet is far more than just a mere physical property. It's a fundamental architect of habitability, weaving together climate, energy distribution, and potential for life. Mars offers a stark example of what happens when planetary motion slows. As its core cooled, its magnetic field disappeared, allowing solar radiation to strip away air and water. Only faint traces remain in its crust, ghostly reminders of a once dynamic world. Venus provides another dramatic illustration. Rotating backward and incredibly slowly, completing just one rotation every 243 Earth days, it has almost no magnetic field. Its thick carbon dioxide atmosphere traps heat in a runaway greenhouse effect, making it the hottest planet in our solar system. Recent scientific observations have begun to illuminate these dynamics. Using the James Webb Space Telescope in 2023, researchers examined exoplanets like WASP-39b and TRAPPIST-1e. They discovered that planets with measurable spin or atmospheric circulation demonstrate clearer chemical balance and more stable temperature distribution. A 2021 study from the Harvard-Smithsonian Center for Astrophysics added crucial insights. Exoplanets with rapid spins tend to maintain molten metallic cores longer, which extends the life of their magnetic fields. These fields shield atmospheres and potentially increase the likelihood of surface liquid water, a critical ingredient for life. NASA's Exoplanet Exploration Program confirms rotation's critical role in determining a planet's climate and habitability. The relationship between spin and planetary conditions runs deep. Rotation shapes day length, temperature gradients, atmosphere, weather, and magnetic protection. Life, it seems, doesn't just survive despite planetary motion, it thrives because of it. Our world's rotation has changed over eons, yet its effects continue to resonate. It controls tides, forest growth, and animal migrations. It defines our sense of time not as an abstract concept, but as the physical turning of the world beneath us. As astrophysicist Neil deGrasse Tyson eloquently noted, "We are not just in the universe, we are of the universe. The Earth turns, and so do we." When rotation reaches its limit, it stops being motion and becomes distortion. At extreme speeds, turning objects no longer just move through space. They begin to pull at time itself. Einstein's general theory of relativity, published in 1915, predicted that gravity and motion are inseparable, two expressions of how mass curves space-time. The greater the energy or spin of an object, the more it twists the geometry around it. This twisting of space-time by rotation is called frame dragging, and it's one of the most subtle, beautiful, and verified predictions of modern physics. Space-time can be viewed like a calm lake. When a massive object spins like the Earth or a black hole, it stirs that lake, creating tiny vortices in the very flow of time. In those whirlpools, the direction of time itself can begin to curve. NASA physicist Francis Everett, who led the gravity probe B experiment, described it as similar to how a spinning sphere twists honey. The Earth rotates and drags space-time around with it, much like that honey twisting motion. Gravity probe B, launched in 2004, used 4 ultra-precise gyroscopes orbiting 400 miles above Earth to measure this effect. After a year of observation, NASA confirmed that our planet's rotation drags spacetime by about 0.012 degrees per year. That may sound small, but it matches Einstein's equations with extraordinary precision. Even our gentle planet spinning once every 24 hours is capable of bending the flow of time. If Earth stopped spinning tomorrow, the oceans would surge toward the poles. The atmosphere would collapse into chaos, and the planet would lose its breath. But tonight, as it spins gently beneath you, everything still works perfectly, quietly, continuously. Perhaps it's no exaggeration to say that the rotation of Earth is the quiet architect of life. The same cosmic motion that once swirled dust into a planet now spins that planet into morning, into wind, into rain, into you. Now, as we drift deeper into this journey, let's follow that rotation outward to where spinning no longer shapes life, but begins to bend something even stranger. Because beyond a certain speed, rotation doesn't just move matter. It can start to twist time itself. Imagine a rotation billions of times faster and a gravitational field billions of times stronger. That's what happens near a neutron star. When a massive star dies, it collapses under its own gravity, squeezing matter into an incredibly dense object. This is where our next chapter begins. Part 4. Can rotation bend time itself? When neutrons form from protons and electrons merging, something extraordinary happens. These stellar objects measure just 12 miles wide, yet they outweigh our sun dramatically. Their rotation defies imagination, spinning up to 700 times each second. Astronomers named them pulsars, drawing from their lighthouse-like radiation beams sweeping across space. During rotation, they generate the universe's most intense magnetic fields, warping space-time so violently that light itself struggles to travel in straight paths. The spinning creates gravitational time dilation, a phenomenon Einstein explained where time runs differently under extreme conditions. NASA's instruments aboard the International Space Station have mapped these space-time distortions, revealing that time near a pulsar ticks more slowly than on Earth. Spinning bodies, especially black holes, dramatically demonstrate this effect. Kerr black holes, named after mathematician Roy Kerr, who first solved their theoretical equations in 1963, represent perhaps the most exotic cosmic structures known. Unlike stationary black holes that simply pull inward, Kerr black holes actively spin space-time around their axis. Near their event horizon, rotation approaches light speed. Nothing can resist being dragged along, not matter, not even time itself. The surrounding region, called the ergosphere, becomes a realm where no object can remain stationary relative to distant space. Every particle and photon must rotate with the black hole, transforming space into a vast, invisible whirlpool. In 2021, NASA's Chandra X-ray Observatory provided direct evidence by observing matter spiraling around a black hole in galaxy M87, confirming predictions about relativistic rotation. Within this cosmic maelstrom, time behaves radically differently. Hypothetically, if one could hover near the ergosphere, time would pass at a dramatically different rate. Minutes for an observer could translate to hours elsewhere in the universe. Einstein described this as time's fundamental warping, a direct consequence of how motion and gravity interact, reshaping our understanding of reality's most fundamental dimensions. Einstein once wrote that time and space are modes of thinking, not conditions of existence. In 2019, the Event Horizon Telescope captured the first image of a black hole's shadow, and by 2022, it had released an image of Sagittarius A, the supermassive black hole at our galaxy's center. The luminous ring we observe isn't light from the black hole itself, but from matter spiraling around it, with light bent and delayed by space-time curvature. These glowing arcs visually demonstrate how rotation and gravity can bend not just light, but the flow of time itself. This phenomenon isn't limited to extreme cosmic events. Even satellites orbiting Earth experience tiny time differences. The Global Positioning System, GPS, must constantly correct for gravitational and velocity-induced time dilation. If left unadjusted, GPS clocks would drift by 38 microseconds daily, enough to cause navigation errors of several miles. Astrophysicists' simulations of regions near rotating black holes reveal mathematical wonders. Rotation can twist space-time so sharply that closed time-like curves might appear, theoretical paths where a particle could loop back to an earlier point in time. While the physical reality of these loops remains uncertain, they emerge naturally from Einstein's equations. In these extreme environments, past and future lose their fixed meaning. The James Webb Space Telescope now observes distant quasar accretion disks powered by supermassive rotating black holes. Its infrared spectra show light stretched and redshifted, indicating time runs slower in these regions. Some detected light left these spinning giants over 13 billion years ago, allowing us to watch time itself stretched across the cosmos. Rotation doesn't just shape matter, it defines how time flows near it. The faster and denser the spin, the greater the warping of space-time. From our gentle planet to the violent hearts of galaxies, the universe uses spin to sculpt both motion and time. What we call now varies everywhere, depending on how fast and deeply local space-time is turning. Even light, typically traveling at the universe's ultimate speed limit, is forced to bend and slow near rotating masses. NASA's Chandra and XMM Newton missions have captured X-ray echoes around black holes, light briefly trapped in rotation, further illustrating the profound relationship between motion and time. End time stretches in strange, elastic ways, measured yet unpredictable. Rotation might twist the universe itself across vast cosmic scales. ISA's Planck satellite data doesn't conclusively prove universal spin, but hints remain tantalizing. Subtle cosmic rotations could influence time's flow across billions of light years. Even faint whispers over immense distances might leave traces in ancient light's polarization. Physicist Kip Thorne, known for his work on interstellar science, explains how near a spinning black hole, an observer's future could become another's past. Rotation doesn't just bend paths, it warps the entire sequence of events, altering existence's fundamental rhythm. Yet this effect remains consistent and measurable. Atomic clocks aboard aircraft, satellites, and mountain laboratories have verified time dilation around rotating bodies. The faster you move or deeper you fall into gravity, the slower time progresses. This isn't an illusion, but the universe maintaining a perfect balance. Rotation's ability to bend time follows a smooth universal law connecting motion, gravity, and energy into one continuous system. From Einstein's equations to every ticking satellite, one truth emerges. The universe doesn't just move through time, it creates time through motion. Right now, your personal time experience connects to Earth's gentle spin, the sun's gravitational pull, and the galaxy's rotation. Motion so precise it literally writes the seconds of your life. Electrons rotate inside atoms. The Earth turns once every 24 hours, dragging space-time enough to alter time's flow. At the equator, where Earth moves fastest at about 135 clocks run slightly slower than at the poles. This isn't due to temperature or air pressure, but relativity. Einstein's theory revealed how motion fundamentally shapes temporal experience. The mystery continues. If spin controls time, who or what controls the spin? Every second you live is shaped by motion. Your watch, atomic clocks, even your heartbeat depend on something spinning. Tonsprinter gravity stretches and compresses time, depending on how fast and deep you are in a gravitational field. But who or what controls spin? Scientists turn to atomic clocks, humanity's most reliable timekeepers, to answer this question. Deep inside these instruments, electrons orbit atomic nuclei at fixed energy levels. When electrons jump between these levels, they emit photons at a precise frequency. The International Bureau of Weights and Measures defines 1 second as 9,192,631 cycles of radiation from the cesium-133 atom's ground state transition, essentially calibrating every moment of our lives to a tiny atomic spin. Quantum mechanics reveals that electron rotation isn't physical spinning, but a fundamental matter property. Particles carry spin values that determine their behavior in magnetic fields, chemical bonding, and compliance with the exclusion principle, the rule preventing two electrons from occupying the same quantum state. Timekeeping, at its smallest scale, depends on atomic spin's internal angular momentum. But spin's influence extends beyond laboratories. Planetary rotations govern cosmic time. Earth's rotation defines a day's length, while its solar orbit determines a year. These motions aren't static, they drift. Tidal forces from the moon gradually slow Earth's spin, adding 1.7 milliseconds to each day every century. To maintain synchronization between atomic and planetary time, scientists use leap seconds, periodically adjusting atomic clocks. Clocks at different latitudes reveal fascinating time variations. A clock at sea level near the equator, moving fastest due to Earth's spin, runs slightly slower than one high in mountains or near poles. This demonstrates special and general relativity in action. NASA explains that an equatorial clock ticks more slowly because it moves faster and deeper in Earth's gravitational potential. The difference is minuscule, a few nanoseconds daily, but measurably real. Even GPS systems must account for these variations. NSN GPS satellites orbit Earth at about 8,700 miles per hour, soaring 12,500 miles above the surface. Their high-speed journey creates unique time-related challenges. Onboard atomic clocks run faster due to weaker gravity and increased velocity, gaining about 38 microseconds daily. Without correction, navigation errors would quickly accumulate to several miles. Engineers solve this problem by blending Einstein's theoretical equations with real-world measurements. They adjust for spacetime's curvature caused by Earth's rotation, ensuring precise timekeeping. Every location signal and map check demonstrates relativity in action, a silent dance between gravity, motion, and spin. The origin of this cosmic spin traces back to angular momentum, a fundamental physics principle. When our solar system emerged 4.6 billion years ago, a collapsing gas and dust cloud began spinning. Like a skater drawing her arms inward, the shrinking mass rotated faster. This primordial motion distributed angular momentum throughout the solar system, to the sun, planets, and moons. No external force continuously maintains this rotation. Inertia keeps celestial bodies spinning, similar to how a plane remains in motion until something interrupts it. In the frictionless environment of space, these spins can persist for billions of years. Spin, in essence, governs itself. The connection between spin and time becomes increasingly complex at different scales. Atomic spin determines energy states. Planetary spin defines days. Cosmic spin warps time itself. These levels interconnect through one fundamental law: angular momentum conservation. Time isn't an independent entity, but a reflection of energy and spin interactions. In 2016, NASA's Gaia mission mapped over 1 billion stars, revealing our galaxy's rotation, a complete turn every 230 million years. Each stellar orbit contributes to a grand cosmic timepiece, marking galactic time. Just as atomic spin defines seconds, stellar spin defines eons. The Sun itself demonstrates this complexity, rotating once every 27 days at its equator, but not uniformly. Its poles rotate more slowly, a phenomenon called differential rotation. This twisting motion generates magnetic fields that shape solar flares and coronal mass ejections. The universe spins without external control, a self-sustaining mechanism of perpetual motion. Magnetic storms sweeping toward Earth don't just graze our planet's surface, they twist our magnetic field and can wreak havoc on satellites and power infrastructure. Spin isn't some passive background phenomenon. It actively shapes fields, defines rhythmic patterns, and interacts with the very instruments we use to track time. Einstein's relativity revealed a profound connection. In his groundbreaking equations, spacetime's geometry is intimately tied to energy and momentum, including angular momentum. Essentially, spin curves time itself. Remove spin, and spacetime becomes flatter and less dynamic. Reintroduce it, and time warps, gently for planets, violently for black holes. Time might be understood as a recording of motion. Atomic spins mark seconds, planetary rotations define days, and galactic spins measure cosmic epochs. Everything that moves measures, and everything that measures moves. The universe's earliest moments already contained this fundamental principle. In 2022, the James Webb Space Telescope peered back over 13 billion years, detecting rotation in primordial galaxies. This suggests angular momentum existed almost immediately after the Big Bang, meaning the connection between spin and time has been operational since the universe's first seconds. Spin doesn't emerge from time, it's what gives time its flow. If spin naturally arises from motion's conservation, who or what ultimately controls it? Science's most precise answer is refreshingly simple. The universe controls itself. Every spin finds its balance. Every slowing motion is compensated elsewhere. From the smallest quantum particle to vast cosmic structures, the same equations ensure angular momentum remains perfectly conserved across space and time. NASA's Jet Propulsion Laboratory captures this elegantly. The laws of motion remain constant. The universe operates on balance. What's lost in one location is gained in another. There's no master clock, no hidden controller. Motion maintains its own timing. Spin serves as the universe's internal gyroscope, keeping everything aligned. From atomic scales to stellar expanses, the same principle governs. When systems decay, collide, or decelerate, their angular momentum transfers onward, perpetuating the cosmic rhythm. Who controls spin? The universe's answer is subtle yet profound. No one must. Motion sustains itself. This quiet balance underlies both time and existence. Your very atoms spin in harmony with Earth's rotation, connected to a vast, intricate dance of motion. An orbiting moon, spiraling galaxy. We're already part of a motion that transcends understanding. Every heartbeat is a fraction of a universal rhythm that began long before time itself could be measured. The cosmos holds a profound question. What happens when perfect balance is disrupted? At the universe's beginning, perfection wasn't the starting point. Instead, a tiny imperfection sparked everything. Physics explains symmetry as nature's consistent behavior in all directions. When symmetry is absolute, nothing changes. But when it breaks, even slightly, motion emerges and structure takes shape. NASA's Goddard Space Flight Center reveals how the universe exists precisely because perfect symmetry didn't persist. In the first moments after the Big Bang, The early universe was an incredibly hot, dense plasma, where fundamental forces, gravity, electromagnetism, strong and weak nuclear forces, were once unified. As the universe expanded and cooled, these forces began to separate through a process called spontaneous symmetry breaking. This mechanism shaped everything from atomic structures to the very fabric of space-time. The Planck mission mapped the cosmic microwave background, the faint afterglow of the Big Bang, and discovered something remarkable. Despite being astonishingly uniform, it wasn't perfect. Tiny temperature variations, just 1 part in 100,000, revealed the first signs of broken symmetry. These minute energy density differences would eventually grow into galaxies, stars, and planets. Without such fluctuations, the universe would remain a smooth, static, featureless mist. Matter's very existence depends on broken symmetry. In the universe's youth, matter and antimatter were created in nearly equal amounts. The key word is nearly. For every billion antimatter particles, there were 1,000,000,001 matter particles. This slight imbalance, called baryon asymmetry, meant that when matter and antimatter annihilated each other, a tiny fraction of matter survived, ultimately giving rise to everything we know. End particles and matter emerged from the universe's earliest moments, shaped by subtle imbalances that gave rise to everything we see today. Nobel Prize winners James Cronin and Val Fitch uncovered a critical discovery in 1964, CP violation, which reveals that fundamental physics treats matter and antimatter with slight differences. Without this asymmetry, the universe would contain only light. Imperfection, in essence, made everything possible. At CERN, scientists continue investigating this phenomenon through the Large Hadron Collider, exploring particles like the Higgs boson that play a crucial role in breaking symmetry. Approximately 10 to the power of 12 seconds after the Big Bang, when the universe cooled, the Higgs field gained a non-zero value across space. This field gives particles mass and separates light from matter. It essentially froze the universe into its current form, locking in the differences that enabled complexity. Symmetry breaking isn't always dramatic. Sometimes it's as simple as a balanced pencil falling in one direction. Similarly, time's direction might have emerged from a tiny initial fluctuation, perhaps in entropy or quantum probability, that pushed events forward. Physicist Shaw Carroll describes time as a measurement of how far we've drifted from perfect symmetry. The cosmic web's vast structure of galactic filaments arises from these early imbalances. JWST's deep field images reveal galaxies forming along dark matter threads that trace the earliest quantum density variations. Billions of years from now, the Milky Way and Andromeda will merge in a slow, silent fusion. Their combined rotation will settle into a massive, nearly motionless elliptical galaxy. Yet spin doesn't truly vanish, but transforms, continuing its cosmic ballet of energy and motion. Net-end stars fade. When a massive star dies, it collapses inward, spinning faster as it conserves angular momentum. This spinning process creates neutron stars, city-sized objects rotating hundreds of times per second. NASA's NICER instrument on the International Space Station has tracked pulsars spinning 716 times per second, with their energy beams sweeping through space as precisely as atomic clocks. Yet these cosmic lighthouses aren't eternal. They gradually slow down, radiating energy through gravitational waves and magnetic fields. As time expands, rotation becomes increasingly scarce. Black holes represent the last great engines of spin. Stephen Hawking predicted in 1974 that even these cosmic giants aren't permanent. They leak energy and lose angular momentum across unimaginable timescales. A spinning black hole, known as a Kerr black hole, transfers its rotation to surrounding space, leaving faint energy ripples stretching across the universe. The LISA mission, planned for the 2030s, will detect these gravitational whispers, waves generated by merging and fading black holes. Each detection will record rotation being released into space-time, echoing across billions of light-years. Even after the black holes disappear, their rotational memory will remain imprinted in the universe's geometry. Will the universe ever completely stop spinning? Not exactly. Angular momentum can't be destroyed, only spread thinner and shared among an expanding sea of particles. NASA explains that in an isolated system, angular momentum is conserved. The universe never truly stops moving, it only redistributes motion. In the far future, after stars have died and galaxies faded, the universe will enter what physicists call the heat death. Energy will become evenly distributed. No temperature gradients, no flow, no reason for movement will exist. Rotation will persist mathematically, but without contrast or structure, it will lose meaning. Cosmologists like Lawrence Krauss and Brian Greene describe this as the cosmic silence, the final calm after every vibration, orbit, and spin. In this distant epoch, protons might decay, and black holes may dissolve into radiation bursts. Only faint background photons and neutrinos will drift endlessly through space, carrying the last traces of motion. The James Webb Space Telescope reveals deep insights into both the universe's past and its potential future. Its images capture the intricate dance of motion that defines cosmic structure. Ancient galaxies appear like ticks on a cosmic clock, showing how rotation once shaped everything. Each observation unveils beginnings and endings, revealing motion sparked by imbalance and gradually fading into stillness. Yet spin leaves indelible marks across the universe. From the cosmic microwave background's polarization to the curvature of space-time around dying stars, motion's memory remains encoded in the universe's fundamental design. We haven't lost movement. We've simply lost the ability to perceive its subtlety. Right now, Earth's core continues turning. Stars orbit, and the Milky Way drifts through darkness. Every motion represents a flicker of that ancient rotation, a force that will outlast individual existence. When ultimate stillness arrives, something will remain. Not movement itself, but the memory of movement. Even if the universe forgets how to turn, its geometry will remember its previous motion. As we approach this horizon of stillness, a profound question emerges. What are we? The beings still moving within this slowing cosmos. Our story begins with the motion of consciousness itself. Are we the universe remembering its own motion? Every atom within you spins continuously. Electrons orbit nuclei, protons and neutrons pulse, and quarks deep inside are caught in perpetual movement. This isn't random motion, but a continuation, a faint echo of the universe's first rotation. Your breath, heartbeat, and smallest movements connect you directly to cosmic motion. Physics describes this as angular momentum, the principle that keeps motion alive. It explains why galaxies turn, planets orbit, and atoms vibrate after 13.8 billion years. NASA's Goddard Space Flight Center confirms that angular momentum cannot be destroyed, only transferred or shared. Every spin, from the grandest galaxy to the tiniest particle, continues the original rotation that began with the Big Bang. The universe was never truly still. Measurements from ESA's Planck satellite demonstrate that motion has been fundamental since the beginning. The cosmic microwave background, The faint afterglow of the Big Bang reveals a fundamental truth about the universe's motion. Its subtle temperature variations hint at the original angular momentum that set everything spinning. This primordial spin never truly disappeared. Instead, it fragmented, cascading across scales from massive galaxies down to tiny atoms. The principle of conservation plays out everywhere. When stars form, hydrogen and helium clouds collapse under gravity, spinning faster as they shrink, just like an ice skater pulling in her arms. This rotational memory persists through entire planetary systems. Each planet, moon, and celestial body carries a fragment of that ancient spin. Even deeper, within rocks, oceans, and living cells, the pattern continues. Our atoms themselves hold this rotational legacy. At the quantum level, electrons define chemical bonds through a property called spin. This isn't literal spinning, but a quantum state that determines how particles interact with magnetic fields. Without spin, chemistry would collapse. NASA describes it as the engine of atomic structure, the difference between chaos and order. Every piece of matter carries an ancient choreography. Particle spin generates magnetic fields, which create structure, leading to stars, planets, and ultimately life. Your very thoughts emerge from this cosmic dance. Neurons fire using electrical potentials shaped by these fundamental fields. Each brain wave represents an alignment of charged particles, a type of ordered motion. The connection runs deep. The magnetic fields in your brain echo the same electromagnetic principles guiding distant pulsars and magnetars. As Neil deGrasse Tyson said, "We are not in the universe. We are part of the universe, and the universe is in us." From a scientific perspective, memory is pattern preservation, information encoded in physical states. Atoms remember through spin orientation. Cells remember through molecular structure. Stars remember through rotation curves. And the universe remembers through the geometry of space-time itself. Once Einstein's general relativity reveals how energy and momentum shape the curvature of space-time. Every movement leaves a trace, a subtle swirl in reality's geometry. NASA's Gravity Probe B experiment in 2011 confirmed this phenomenon, known as frame dragging. The probe measured how Earth's rotation twists surrounding space-time, much like a spoon stirring honey. This discovery proved that spin isn't limited to specific objects, but extends into the cosmic fabric itself. Even your tiniest movements disturb space-time, though the scale differs dramatically. Your body's atoms spin billions of times per second, generating magnetic interactions detectable by quantum sensors. These micro-rotations contribute to a motion record that predates humanity. Light itself carries angular momentum. Photons possess a spin that determines how they polarize and interact with matter. Polarization patterns across the cosmic microwave background serve as the oldest record of rotational memory in existence. Missions like Planck and NASA's WMAP have mapped these swirls in extraordinary detail, revealing faint B-mode patterns, signatures of primordial gravitational waves from the universe's first motion. If all motion leaves traces in space-time, perhaps consciousness is how the universe perceives these traces, not as emotion or spirit, but as physical continuity recognizing its own persistence. Consciousness, in a scientific sense, is a system's capacity to reflect its internal state, and that reflection is written in movement. When you gaze at starlight, you're witnessing the memory of spin, light twisted and stretched by billions of years of motion. This light enters your eyes, triggers chemical reactions, and becomes part of your neural motion. The universe doesn't just remember its spin, it continues to experience it through every observer it creates. As the cosmos expands and cools, these traces persist. Galaxies may slow, but their angular momentum never disappears. It transfers to intergalactic gas, dark matter halos, and radiation. The James Webb Space Telescope has detected faint filaments of gas between ancient galaxies, structures shaped by these spin transfers. Every wisp of matter still moves to the rhythm set 13.8 billion years ago. And when the last stars fade and motion becomes silence, those patterns will remain encoded in the very fabric of existence. Gravitational waves, particle spin, and frozen light will continue to ripple faintly through empty space. They aren't gone. Instead, they're etched into the very shape of what remains. Like rotation's fossils, they form the universe's deepest memory, motion preserved as pure geometry. Carl Sagan once captured this beautifully. The cosmos is within us. We are made of star stuff. We are a way for the universe to know itself. Physics reveals this knowing isn't mystical, but fundamental, a continuous encoding and retrieving of cosmic history through motion, energy, and spin. Take a slow breath. Every atom inside you carries the same spin that first ignited stars. You are a moving archive, a living piece of the universe's ongoing memory. Following this idea that motion might be the cosmos remembering itself, a new horizon opens. Perhaps life is that brief moment when the universe pauses just long enough to notice its own spinning. This quiet journey might bring a small moment of peace. Your presence matters, whether through a gentle like, a soft subscribe, or simply listening. In the comments, share where you are tonight, what time it is. I love seeing how these quiet adventures drift across the world, from one sleepy corner of the planet to another. Your words, your presence, even your silence, they're like little stars guiding me forward, and I treasure them deeply. Until next time, may the universe turn softly around you. Moo.